All right, today we're diving into the science of purification. We're going to talk about how chemists take a total mess of a mixture and pull out one single pure substance. It's a massive challenge, but the solutions, well, they're incredibly clever. So, how do they actually do it? I mean, how do you get pure salt from seawater? Or how do you isolate just the caffeine from coffee beans? It all comes down to one big question. How do you separate the one thing you want from all the other stuff you don't?
Now, to talk about this like a chemist, we need a couple of key terms. First, there's the analyte. That's the good stuff, the substance you're actually trying to get. And then there's the interferent. That's, well, it's everything else that's just getting in the way. So the whole game is to isolate the analyte and leave all those pesky interferents behind.
So here's our game plan. First, we're going to look at the one core principle behind every single separation. Then we'll get into the cool techniques that use size, mass, and even changes in physical state. After that, we'll see how some clever chemical reactions can totally change the game. And we'll wrap up with a really interesting twist, a technique that can be both a huge problem and an amazing solution. Okay, let's get right to the heart of it. The entire field of separation science is really built on one simple but incredibly powerful idea.
Here's the golden rule. To separate two things, you have to find at least one property that makes them different. It could be anything, their size, their mass, their boiling point, you name it. Once you find that one difference, you can build a whole technique to exploit it.
You can think of this table as a chemist's toolbox. See how all the major techniques are sorted by the property they go after? We've got separations based on size, like filtration, others based on mass and density, and some that rely on changes in physical state, like distillation. We're going to be exploring some of the most important tools from this very kit. So let's see how this works in the real world. First up, the most intuitive method of all, just separating things by their size. I like to call this the bouncer principle. You know, some molecules get in, while others are just too big to make it through the door.
The idea here is just beautifully simple. All you need is some kind of barrier with holes in it, a porous medium. If your analyte can squeeze through but the interference can't, or maybe it's the other way around. Boom! You've got yourself a separation.
And there are three major ways we do this. Filtration is probably the one you already know. It's just like making coffee. Then there's dialysis, which uses a special membrane with super tiny pores. And size exclusion chromatography is a really slick technique that uses a column packed with porous beads to basically slow down the smaller molecules. And believe me, this isn't just some abstract lab technique. This stuff is vital. Like the slide says, in kidney dialysis, a membrane is used to separate tiny waste molecules from the much larger essential blood cells and proteins. This simple idea of separating by size, it literally keeps people alive.
Okay, so what if size isn't the big difference between your substances? Well, our next set of tools uses differences in mass, density, or even physical state. You know, whether something's a solid, a liquid, or a gas.
First up, we've got centrifugation. You put your sample in a tube and just spin it incredibly fast. It's kind of like being on a merry-go-round. The heavier or denser stuff gets flung outwards, or in this case, down to the bottom of the tube, way faster than the lighter stuff.
Next is distillation, which is a super powerful way to separate liquids that have different boiling points. Let's trace the process on this diagram here. You start with your liquid mixture at point A. When you heat it, the stuff with the lower boiling point turns to vapor first. That gets you to point B, a vapor that's now richer in that one component. Then you cool that vapor and it condenses back into a liquid at point C. See how we've moved to the left? We're closer to a pure sample. You just keep repeating that cycle and you get closer and closer to perfectly pure.
So how do you do all those cycles efficiently? Well, the setup on the left is simple distillation. It works, sure, but it's not super precise. The real magic is on the right, with fractional distillation. You see that tall column packed with beads? That's the game changer. It creates a huge surface area, essentially letting thousands of little mini distillation cycles happen as the vapor rises. This is the exact principle that oil refineries use to separate crude oil into gasoline, jet fuel, and all its other parts.
But what if your analyte is a solid? Well, for that, there's a fantastic technique called recrystallization. This image gives us a great bird's-eye view of the whole process, taking you from a messy solid all the way to beautiful, pure crystals. Let's break down how it works.
The real trick to recrystallization is finding a solvent where your analyte dissolves when it's hot but not when it's cold. You dissolve the impure stuff in that hot solvent, then you filter out any gunk that didn't dissolve. As the solution cools down, your pure analyte starts to crystallize out, but all the soluble impurities, they get left behind in the liquid.
One last filtration, and you've collected your pure, clean crystals. This exact, precise process is how pharmaceutical companies make the ultra-pure active ingredients that go into many medicines.
So far, we've only really been messing with physical properties like size and boiling point. But what happens when there isn't a useful physical difference to exploit? Well, that's when you turn to chemistry itself and use a reaction to fundamentally change either your analyte or the interference.
Now, it's really important here to not confuse recrystallization, which we just saw, with precipitation. They might sound similar, they both make a solid from a solution, but they are total opposites in terms of purpose. Recrystallization is a slow, careful, selective process that builds pure crystals. Precipitation is just a rapid, non-selective crash, where a solid just dumps out of the solution. It's messy, and it doesn't purify anything. One is an art form, the other is basically just making a mess.
And that brings us to our final section, and to one of the most interesting twists in separation science, a phenomenon that can be a chemist's absolute worst nightmare, and also their most powerful tool.
It's called co-precipitation. Here's what's happening. You're trying to precipitate your analyte to get a nice, pure solid. But some of those pesky, soluble interferents get accidentally trapped and dragged down along with it, contaminating your final product.
And this is where we see its two faces. On one hand, it's a huge problem. If you're trying to measure the mass of your product, those trapped impurities are going to throw off your results completely. But, on the other hand, it can be an incredibly powerful tool. Imagine your analyte is so diluted that it won't precipitate on its own. We're talking about trying to find a few radioactive atoms in a swimming pool full of water. You can actually add a carrier substance that will precipitate, and you can get it to intentionally drag your trace analyte down with it. It lets you collect something that was otherwise impossible to get.
This contamination can happen in a few main ways. With inclusion, an impurity atom literally takes a spot in the crystal structure. With occlusion, you get little pockets of impurities that are physically trapped as the crystal grows up around them. And with adsorption, the impurities just kind of stick to the outside surface. Understanding these is how chemists learn to either minimize the problem or, when they need to, maximize it.
So what's the big takeaway from all this? It really all comes back to that golden rule we talked about at the beginning. The entire art and science of separation is a game of finding and exploiting differences. It doesn't matter if it's size, density, boiling point, or solubility. All you need is one key distinction to turn a chemical mess into a masterpiece.
From the silicon inside our computer chips to the medicines we take, all these techniques are responsible for the pure materials that make our modern world possible. And that leaves us with a final big question. As we start designing new nanomaterials, complex biologics, and sustainable resources, what brand new separation challenges are waiting for us, and what new techniques will we have to invent to solve them?